Shivang Thakkar, registration number 298.
Rahul Singla, registration 299.
Rishav Goswami, registration number 303.
Topic is system model in deadlock.
So now let's start with introduction to deadlock. A deadlock occurs when a set of processes are completely blocked because each process holds a resource but is simultaneously waiting for another resource that is currently held by different processes in the same set. A classic example is process 1 holding resource 1 and waiting for resource 2 while process 2 holds resource 2 and waits for resource 1, so neither can proceed. Now we can see in the system model overview which defines how processes interact with resources. This model includes key components, processes like P1 and P2, resources R1 and R2, and specific number of resource instances, which is a fundamental assumption showing fixed number of resource instances. In the next slide, we can see that resource allocation graph is a visual tool that models this interaction. It uses two types of edges, a request edge P2R showing a process requesting a resource, assignment edge R2P showing a resource allocated to a process. It is a cycle which indicates a potential deadlock, meaning processes are indefinitely waiting for each other's resources. Now we can see in the flowchart that how an RAG is built, which includes process 1 and its individual resources. Now, in the next slide, we can see that there are essentially four conditions which are needed to identify the Coffman conditions for deadlock, which include mutual exclusion. One process can use a resource at a given time, hold and wait. A process holds at least one resource while it waits for another resource. No preemption. Resources can be forcibly taken away from a process. Circular wait, which is a circular chain of waiting process existing where each process waits for a resource held by the next process. Here it is a flowchart which shows the same, which includes mutual exclusion, hold and wait, no preemption, and circular wait. In this example scenario, we can see that P1 holds resource 1 and requests R2, and vice versa, P2 holds resource R2 and requests R1. So the observation we can see is that each process is waiting for a resource held by each other, so neither can proceed. So as a result, it forms a circular chain of waiting processes, which finally leads to and block definite condition of deadlock. Same, it is an example which is visualized by graph for similar processes like P1, P2, and P3.
Now I'll be explaining deadlock handling approaches. There are four key approaches. The first one is prevention, the second is avoidance, third is detection, and fourth is recovery. In prevention, it stops deadlocks for ensuring at least one of the necessary conditions. And second, allocate resources carefully at runtime to keep the system at safe state, preventing deadlocks before they occur. In deadlock, they happen, but check the system periodically to find them. And in recovery, after detection, resolves deadlocks by terminating processes or preempting resources to break the cycle. Now we'll be seeing a flowchart upon deadlock handling, and it will be telling the overview about. First, after the prevention and avoidance, it helps in detecting that if the system is in a safe state, then it will go. But if it's in unsafe state, then it waits. Now I'll be explaining in detail about deadlock prevention. It ensures one of the components condition is broken. For example, eliminate hold and wait request all at once, eliminate circular wait, and process resources ordering. Now this is a flowchart upon deadlock prevention. For example, process 2 is currently handling with resource 2, but it's waiting for resource 1. Simultaneously, process 1 will also be assigned with resource 1, but will be waiting for resource 2. Now, deadlock avoidance. It basically follows the banker's algorithm. First, it checks if there is a need and availability. Then it will help in checking the safety and unsafetyness of the request. If it's safe, then it will grant the request. If it's unsafe, it processes to wait. Now, this is a flowchart here which tells you that if if the need request is successful, then it will go for checking the availability. If the availability is also successful, then it will all hold upon the safetyness and unsafetyness. If it's safe, then it will allocate. If it's not safe, then it will wait. Now I'll be explaining a little about the example of Benger's algorithm. To solve this problem, we need three steps, which is to calculate the need matrix, initialize, and check for a safe sequence. In calculate the need matrix, we need to use the formula need is equal to max minus allocation. In step 2, we need to initialize. In initialize, we have to see if the need is smaller than availability. If it's not smaller than availability, it will not execute. If it's smaller than availability, then it will execute. In the third step, we need to check for a safe sequence. It means that after we have checked that the need is smaller than availability, we need to add it with the availability of process 1. The availability of process 1 is 200. And if it's successful, then it will plus with P1 and the existing available.
Deadlock detection. Sometimes preventing deadlocks completely isn't so practical, so the system allows them to occur and detects when they happen. In this flowchart, we build the RAG based on which processes holds or requests resources. Next, the system checks for cycles. If a cycle is found, deadlock exists. If not, the system is safe. And for deadlock recovery, after detection, the system must recover. For that, we follow two main methods. Process termination, where ending one or more deadlock processes to release resources, and resource preemption, where we temporarily take resources from some processes to let others continue. In this flowchart, we detect a deadlock, select a victim process, abort or preempt resources, and then resume the others. In this graph, we see how system safety status works. And then, as for real-life examples, in databases, two transactions may hold each other a lock that the other needs. Both needs to wait forever. In operating system, two threads can each hold an I/O device and wait for each other's, causing a freeze. In summary, deadlock equals resource contention plus 4 allocation. Steps to manage deadlock are shown below. So this is the methods we can take to handle deadlock: deadlock prevention, deadlock avoidance, deadlock detection and recovery, and deadlock ignorance. These are the resource references we used.